When it comes to learning abstract shader math, I can't think of a more fitting challenge than SDFs. Maybe that's just because I spent over 100 hours working on them, but I do think they are an incredible tool for teaching and problem solving. And if you're remotely interested in making them, or just learning about them, I'd super recommend reading Inigo Chies's catalog of SDF primitives. This page is at the very heart of what we're doing today, and we'll rely on some of his work to make this effect. But first, spoiler warning, this video is going to end up being pretty advanced, but I'll commit to a chapter system so you can just skip to the things you find useful. And if you need some help, I'm sure I or another viewer can help answer questions in the comments, and vice versa if you spot things you can help me with. Alright, so what is an SDF? SDF stands for signed distance function. It takes these input coordinates and returns a map of values. Higher values denote a greater distance from our defined shape. And conversely, the lower the value of a spot on this map, the closer it is to the shape. And once we reach a value of 0, we have no distance from the shape, meaning it returns the exact shape we have defined. But what about negative values on an SDF? Well, that's where the signed part of the SDF comes in. In this case, sign doesn't have anything to do with the wave. It's actually much simpler than that. The sign of a value is positive or negative, unless the input is 0. And the sign operation outputs a positive 1 for positive values and a negative 1 for negative values. That's why, on a signed distance function, every point inside the shape has a negative value. And just like the exterior of our SDF, the farther these points are from their bounding edges, the greater their value. And what that looks like is just going inside of the shape even further. But so far, we don't have a reason to make SDFs, so what are they used for? There are actually quite a few uses for SDFs, but one of the most common and flashy ones is for rounding shapes. Let's take another look at our SDF view of a square. One thing we can notice is that the interior gradient generally has sharp corners, and the exterior, all values above 0, follow some kind of rounding curve. But it's easy to misinterpret what I just described as a rule of SDFs, where the inside of a shape has sharp corners between gradients, and the outside has these nice rounded corners. But what this actually depends on is convexity and concavity, and it's completely separate from whether the corner is inside or outside the shape's boundary. Many shapes we describe, like regular polygons for example, are concave on the inside and convex when viewed from the outside. But on Inigo's page, we can see an example of the opposite. The middle portion of this cross shape has a rounded gradient on the inside, since it has convex internal corners that are rounded further with the SDF. Similarly, we see sharp corners of the SDF on the outside of the shape, shown in these 4 spots. But alright, if this is all new to you, you probably have a lot of questions. Unless you find it boring, where you can click off the video about now. Nice choice, thanks for staying. Going forward, I'd like to introduce you to Inigo's names for these different parts of the SDF. And yes, this Inigo guy really is synonymous with SDFs. Firstly, we've got the isosurface. Each isosurface can be seen with a compare node, or just with the SDF viewer. Isosurfaces are these loops that go around the defined shape, and they look like onion rings layered inside and outside the shape. Each isosurface has its own value, and as we've discussed, their values represent their distances from a shape. The 0 isosurface is equivalent to the boundary we've discussed too, shown in white with the SDF viewer. Okay, I hope this hasn't been too much so far, and I hope I haven't bored the advanced users to death yet. But let's step it up quite a bit and learn how we can make these SDFs for ourselves. Most SDFs take advantage of vectors for optimization, but don't let that scare you as a beginner, because there's still an easier way to make some of them with only float values, which are these gradients. For example, say we wanted to make just a corner SDF, coming in from the left, dropping down at the middle with a rounded turn in between. The easiest way to make this would be to use a vector maximum operation, and then a vector length operation. And as we can see, this returns a correct corner SDF. But under the hood, it's really just one quadrant of a circle SDF. To prove that it is really a circle, we can remove the maximum operation right before our length operation. Now technically this is the SDF of a point, but after a subtraction that's functionally identical to the SDF of a circle. So here we can easily visualize how that stretching on the x and y works. But how do we convert this map of x and y values into a map of float values? More specifically, what I'm asking is how this length node works. The vector length operation takes input vectors and tells us how close they are to 0 on all axes. And since these high x and high y values intersect in the top right of the map, it's colored to be brighter since it's farther away from 0 on all axes. This intersection of axes is really important, since it's what gives a lot of SDFs their rounded shape. But okay, before we move on, I did promise there was an easier way to get this exact effect, and it does not use vectors at all. Let's go back and add our max node to remove negatives, once again stretching this imaginary circle. Then, instead of a length node, you can separate the x and y axis of the system, square them separately, and add them together. And doing that, you'll get a squared version of the length from before. And this isn't necessary, it's really up to you, but you can always just take the square root of this gradient to make it linear again, which in some cases makes it much easier to work with and more accurate. And for doing that, congratulations, you've just graduated from beginner to intermediate. Now that you know what we need to make an SDF, let's go over the main point of this video. You see, I'm trying to make a triangle SDF defined by 3 control points. Fundamentally, all we need is a gradient defined by these 2 points. It should span across them like this, and crucially, it should always have a clear positive and negative side, no matter the configuration of the 2 points. And if we do this for all 3 sides of the triangle, we get 3 really useful gradients. These gradients give us enough information to give us the negative portion of our SDF. Keep in mind that making the interior and exterior components of the SDF separately is standard practice. It's not just a hack that approximates a working SDF, it's the correct technical approach. We usually don't have one final operation that gives us the positives and negatives. We usually make them independently and add them to one another, even in the case of a simple square SDF, as discussed in my last video. Speaking of, through my last video's comments, I was made aware of a new way to pipe in position information into a shader. Earlier, I used a driver setup for the X and Y components separately, but it was brought to my attention that using attributes through GeoNodes is quite a bit more performant and a little sleeker in the shader editor. But alright, no matter how you're connecting positional information, there's still quite some work ahead of us. And as a tip, here are some key things to remember. Subtracting our object coordinates by a location shifts the original coordinates to that position. That alone isn't very helpful, but it will be soon, so try to keep it in mind. And already, with our controller positions connected to the shader, we can easily make some handles to draw circles using dot product. But what if we flip this to a cross product? Oh, would you look at that? This seems to be just what we need. And now, if we separate the z-axis after this operation, we get the exact gradient we want. So no matter the orientation of our points, cross product keeps its signs. Hey, sorry to interrupt, but I actually missed something in recording. It's something that I do mention later on in the video, but I wanted to mention it here to get it out of the way and to make things clear. So these gradients, when combined, look pretty good, but if you bring them together, you'll notice that they actually scale down. So I'm actually going to zoom out and solve this for just one of the sides to show you how you can apply this to all 3 of them. So here we have our cross product gradient between the 2 empties, and just as I mentioned earlier, the closer they are together, the more this gradient seems to become dimmer in both the positive and negatives. So what we're looking for is information that tells us how close these 2 empties are from one another. And to get the distance output from these 2 vectors, you might be able to guess already that we'd use a vector distance node, with both points connected to the sockets. Now, the closer these 2 points are, the lower this output will be, and the farther away they are from one another, the higher it gets. And from here, we can simply take our z output from the cross product and divide by the distance that we just got. So now we've done a process called normalization that keeps this gradient's values intact, making it usable for the SDF. We do use this technique a little later in the video, so stay tuned for that explanation. Alright, thanks for letting me interject. Here's a comparison of the normalized and non-normalized gradients for the interior of the SDF of the triangle. You can see that the distances just aren't accurate when you're using the non-normalized version, and this just wasn't in my script, so sorry about that. But anyways, back to it. So now, if we construct 3 of them independently, one for each of the sides of the triangle, we have enough information to build the interior of the triangle. Now the inside is done, but why can't we use this same system for the outside of the shape? Well, let's try it. To keep it easy to understand, I won't use vectors at all, just squaring the gradient and adding it to other squared sides. And at first glance, this does look really good. But in reality, this is nowhere near the correct system for what we want. What we made doesn't denote distance accurately, and it might seem accurate at first, but let's compare it to a true SDF. Here we can see how the corners are rounded in a stretchy way that looks more parabolic than circular. The isosurfaces at the corners of the triangle should be equidistant from the corner's tip, and not at all bendy like this. The best case scenario for this system would be an equilateral triangle. But even then, the inaccuracy of this rounding makes it not worth our time. By the way, the same applies to the vector-based system. Taking the length of it gives us the same result. But the reason the vector and squared system works on certain shapes is because of the shape's right angles. Remember, for something to be a true SDF, every value must represent the exact shortest distance from the shape's edge. And this gradient doesn't adhere to that rule. But for accurate corner rounding, we need to find a better solution. In technical art, just as in any art, people happen to approach and think of solutions differently. Some might want to spend their week making 2D animations in nodes, and some might avoid that entirely and rely on presets and external tools to help make things quicker. You can probably guess which bucket I fall into, but no matter your workflow, I'd very highly recommend the B3D SDF add-on I've been using. It's published by CMZW, and the add-on is based, at least somewhat, on Inigo's SDF page. I'll leave a link to the GitHub page for it in the description, since it's absolutely free and could open up opportunities for shaders you've never even thought of. The primitives this add-on gives you are really flashy, and there's a lot of them. I'm super impressed with the node graphs as well. They're likely some of the cleanest and most intuitive shaders I've ever seen. In fact, I'd bet that without even using the primitives in your shader, reading the setup for them can come in super handy and allow you to approach problems in ways you haven't thought of before. The same applies to Inigo's page if you can read GLSL, but I can only read node logic. Still, it goes without saying, this add-on is an incredible resource. Here, let me show you. Let's add in a triangle SDF node, connect our 3 points and our coordinates. And now we can enter the node group and see a bunch of stuff. If you'd like, you can definitely expand and preview these to see the underlying process. One of my favorite additions with this toolkit is the line segment. It's a really versatile SDF that can work with itself to create tons of other ones. In fact, I'd like to take some time out of this video to explain this line segment system in depth. And learning about this tool, which we already have functioning right in front of us, might seem like a waste of time to some. So I've left a chapter system specifically for you to skip this part if you want. But if you follow along, I promise you can recreate and understand this segment without using the add-on at all. And for those that choose to stay, let's take a close look at this segment SDF generator. I guess you could call this the segment. Okay, never mind. Now this is a small detail, but it's still interesting. Initially, when I look at the line segment's internal coordinates, I wondered if we might be able to extract some easy axis that would give us the internal gradient we wanted from earlier. And that really would be ideal. It would mean we could do this whole thing in just a handful of nodes. But it turns out that the coordinates output by this system change drastically depending on their input points. And if you're curious about why that happens or how the line segment works as a whole, I'd invite you to join this next part. Okay, so let's take a look at the problem this segment generator is designed to solve. It's made to take 2 points as a vector input and connect them with a line. That sounds simple enough, right? So let's see how it's done. First off, let's visualize our positions. Here we can see our object coordinates have been subtracted by the position of a point. That's the exact same shifting that I mentioned earlier. We'll call this point 1, sitting in the bottom left quadrant, and we'll try to connect it to point 2, over here in the top right quadrant. Let's try to think of this as drawing a line from the bottom left point to the top right, and not the other way around. That's because, to get from one to the other, we simply add to our original point, allowing us to visualize vectors more easily. Though it's important to remember that this works with any configuration of points. To get started, we'll find the difference in the positions of the 2 points. And you might already know that we can get this by subtracting the 2 input vectors. Do make sure that point 1's coordinates are at the top input of this node. Now, if we take the results of this subtraction and add it to the coordinates of point 1, we get the coordinates of point 2. This property is key to what the line SDF solves, since we can now scale this addition to get an interpolation of the positions between the two inputs. And in case you're unfamiliar, interpolation just has to do with estimating values between datasets, and in this case, it just means blending between the two positions. And because of that, we should make sure to treat this scaling value as a blend between the two. So let's keep this input bounded from 0 to 1. Now, you might not believe this, but we're actually halfway done with making the line segment. What we're looking for now is a gradient that spans between the 2 points, like this. The original point we're working with, which you can think of as the anchor point, has a value of 0. And the point we're shifting the anchor point towards has a value of 1. And if we have a linear gradient in between them, we can get a straight line that connects the 2 points. And that's done by feeding that theoretical output we're talking about into this scaling value here, which, like I said, acts as our blending value between the two positions. And already, you might know how to get this kind of gradient. It has to do with checking for the similarity of vectors directed from one point to the other, right? And in any case of checking for a vector's similarity, we use the dot product operation. So now, we can check for vectors from the coordinates of point 1 going towards point 2. Simply by plugging in the subtraction of the two vectors, which is the same as the difference between them, and the coordinates of point 1 into a dot product node. But this outputs the inverse of the gradient that we want. So we'll flip the order of operations for this original subtraction of the coordinates to flip the values of the dot product gradient. Although flipping the order of that subtraction also means you need to flip this vector add operation to a vector subtraction. Or you could just multiply the gradient by -1 to flip it, if you're not trying to do this in the fewest number of nodes possible. But this gradient has another problem. It doesn't account for vectors of lower magnitude in the same way. And all that means visually is that when points get close together, the gradient scales down and becomes less visible. So let's undergo a process called normalization to make sure we keep our values at 1. Let's take the difference between our initial vectors, shown by this subtraction of the points, and feed that into both of the inputs for this new dot product node. Now, this is a mathematical shortcut that does two things. It acts the same way a length operation would, checking for the difference of vectors from coordinates 0, 0, 0, but it also squares that float output. And that's all a bit technical, but all you need to do with this output is divide the gradient by our dot product of the difference. This way, no matter the distance and position of the 2 points, point 2 will always have a value of 1, and point 1 will always have a value of 0, along with all that comes in between, interpolated linearly. And now, we're blending between the positions of the 2 points with a normalized, generalized system that works for any input position. Oh, right, and the last step is to return the length. Well, I don't blame you if that was too high level or if you skipped, but if you did understand that in some applicable way, you passed the advanced portion of this video. But now that the math is over, we can stop thinking about dot products and just plug in the positions of our empties. So if we hook up the lines between our 3 points, we get an SDF for each side. And then to combine all of them, we'll use a minimum operation on 2 of them, and then a third. So there are 2 things to notice here when we add these 3 segments. The outside of our triangle now has correct SDF properties, but the inside has positives instead of negatives. And because we now have both correct internal and external gradients separately, we now just need to combine the 2 separate systems. The most intuitive way to do this is to take our linear SDF gradient, which we made with cross products, take a greater than of it with a threshold of 0, and use that output as a mix factor between the inner and outer systems. However, with this segment system, I've noticed that each segment actually interacts with the other in a way that perfectly mimics the positive version of the internal system. So all you need to do is tell the insides to be negative. This is where that sign operation comes in handy. We can use it to multiply the segment's gradients by the positive outside and the negatives inside. This output is completely functional, and we now have a correct SDF system for a triangle. And whether you choose to mix the inside and outside, or flip the sign of the segments on the inside, is up to you, and makes no difference for the end result. And with all that hard work done, we can now see our very fancy SDF triangle. But what would happen if we move a controller through one of the line segments of our triangle? It looks like the entire internal SDF system just collapses, like that. And that's a little disappointing, considering we've worked so hard on our fancy triangle. So I came up with a system that fixes this exact problem, and rebuilt the internal SDF system. I won't walk you through this solution node for node because this setup needs a lot of optimization and refinement for ease of use. But here's the idea. Our internal SDF system is made up of 3 gradients, one for each side of the triangle. But to combat the fail state I mentioned earlier, we're going to do some checks on the points in relation to one another. More specifically, we're going to look for points that cross an edge and swap certain gradients once that happens. So I did this check once for each side, and now the correct side scales by -1 when they cross a boundary. This is a little advanced noding that I've clumped into node groups. So I'll just skip it for this video and introduce a better solution for this in one of my next videos. But just as usual, I invite you to make your own solution to this arbitrary points problem. Well, whoever's made it this far is truly dedicated, and I'm sure not all of it was easy to learn. I wouldn't blame you if you only got half of it even, that's alright too. Specifically, if you're a beginner looking to make advanced stuff, watching this video until here really means you're putting in the effort, whether you kept up with all of it or not. And for that, I'll leave some simple and kind of miscellaneous tips for the viewers that might not know where to start. My number 1 tip and piece of advice for beginners has to do with the way we see information shown to us in shaders. I think that, at least a lot of the time, we can kind of ignore numbers. By visualizing values as height information, things can become way more intuitive. Here's an example with displacement. I'll take the x and y and use some operations on them in the context of height. Here's a simple start, just adding a constant to x. If we add a mid-level plane, which shows us values or heights of 0, we can see how moving the x-axis shifts their intersection to the left or right. And the same goes for the y-axis, forward and back. But x plus y gives us a gradient rotated to a 45-degree angle between the 2 axes. While going back to our x-axis, we can see how adding a maximum operation of 0 removes the negative height, and how the maximum of x and y together doesn't give a rotated slope, but a folded one. These forms of visualization can really help, and they're universally applicable to any shader. I very highly recommend you just have fun and mess around with math, and discover what you can do with it for yourself. And remember how last video I ended with a challenge for you? Well, this one's got a few too. I can generalize the SDF system in this video into a convex n-gon, and I made it pretty quickly by hand, in about 10 minutes. The triangle we've built is designed to handle convex corners perfectly, but with a polygon with more than 3 sides, we need a way to handle concave corners, which asks us to invert our SDF logic for them. But how can I solve for the interior of an n-gon with concave corners? Convex corners always round outward with this logic, but concave corners need inversion, flipping the logic completely. If you don't solve this, I probably will. Okay, thanks for watching. Consider reading Inigo's work, downloading CMZW's SDF toolkit, downloading some of my free work, or donating to Blender, all in the links below.